Hi friends, so today we'll be building GPT from scratch. So this tutorial I'll show you how to build your own GPT and how you can train it on a custom data set. So for this tutorial, I've taken the movie conversation data set. You can find that here, and specifically I've used the movie lines dot tsv data set. So this basically has the movie ID and who spoke the line and basically the transcription. I'm sorry, the transcript of what was spoken. Right, that's what you would be finding here. What I've done is we are only interested in using this field. So I've combined all the records into one big data set, which is what you would be finding here, a movie dialogue data set. So let it load. So just give it a moment. So what we are essentially trying to build is a model that will spit out movie conversation given a random input. For example, let's say that I tell how beautiful is India. This is a very random statement that I'm making. With its understanding about this whole movie dialogue data set, it is going to spit out a movie dialogue which may be very relevant to the input that I'm giving. Right, so that's basically the idea, a GPT that talks movie dialogue. So that's the whole intention. Now whatever the GPT is speaking from now on, it's not corrected. What I essentially mean to say is it may or may not be relevant to the input that I'm giving, and this is a very small data set that I'm using to give training to this big model. Again, you can use your own data set to train this model, and roughly, right, it's going to scale to a couple of MBs, not even GBs. So that's basically what we're trying to build. And I'm not sure if you know, and GPT is a decoder only model. If you go to attention is all you need paper, there's two segment of the model. One is the encoder and the other one is decoder, and they would be explaining the encoder and decoder part with a sample or an example task of translation, maybe French to English, English to French, whatever, right? But here we are generating characters. Now we are essentially not generating tokens or words here. What I'm going to do is I'm going to train this model with characters, mapped to an embedding that is a real number, and the model will learn to generate characters given set of input characters. So it's going to be no surprise for us if it's misspelling, if it's if it's not spelling a particular token or a word right. So because it is trained on characters, not on words. So, and it is also based on simple embedding, right? I'm not going to use any pre uh, embeddings for characters. It is based on sorting of the vocabulary size, and I'll show you each and every step that you will be seeing here, right, along with how to configure hyperparameters. And finally, we'll try to build a small chatbot using Streamlit. That will also give you an idea of how to deploy this as an application. Now let's proceed with the tutorial. Now that you have an idea of how I've organized this data, so this is basically the architecture that we'll be building. What you're seeing is one decoder block. We'll be stacking close to 6 decoders after the input, right? And then the output is going to remain the same, right? So this is the decoder block, if you will, and we'll be stacking up 6 decoders. And finally, I'll show you what is the structure of the model, what is going to be the input, what are going to be the different layers that are stacked above one another. So we let's proceed. Okay, so if you look at it, so this is the file, and this is the file that I'm reading, and let me show you sample text, maybe 50 characters, right? So you can see, right, they do not, they do too, I hope so. And everything is separated by by new line, right? So what we are essentially going to do is we'll be building an embedding, character level embedding, and it is a very simple embedding. What I'm going to do is I'm going to sort the whole text that it sees right in the document, and I'm only going to take unique characters. We don't need all the characters to build the corpus, only the unique ones. So this is character to embedding, and for inference we would also need embedding to character, because the output is going to be in numbers, so we'll have to have some sort of a mapping for us to convert your characters to, sorry, your embedding to character. So stoi stands for string to integer, and then integer to string. So you can see that I'll be encoding it. This is the encoder bit, sorry, encode bit, and this is decode bit. So now that we have the code to encode and decode a string, let's give it a try. Let me give a couple of examples. So first line will print all the characters, unique characters that it found in the corpus. This line basically tells you what is the unique number of characters. That will be our vocabulary size. You can see these are like 132 132 unique characters, including symbols, right? And yeah, numbers and letters. So it is a very and it also has some sort of encoding, right, found in the corpus, but this is predominantly the characters that it saw in the data set. You can see the vocabulary size is 132. From here on, we'll start to build the model, and I'll explain each and every step. So here we are splitting training and validation. So I'm using 90% of the data set, but it essentially depends on your context. Um, what's up? Okay. I've not imported Torch. Let me import it. One second. Sorry, I should have imported it. So torch.nnn will help us inherit some of the methods from the parent class torch. Now it should work. Yeah, you can see that now I've split your training and your validation data. Now let's get the batch. Let's basically split them into batches, so it'll help us train the model. I'll write a function to do the split in the batch. Now most of the code is based on Andrew Karpathy's video, right? I should credit him for this because the code that I'm writing, it is basically based on what he's written, and I'll be adding some extra code just to make more just to make things more clear. The areas where I found things to hard to understand, I'll make sure with those extra few lines of code, it will help you get a context of what we are doing and get your understanding towards transformer even more deeper. That's basically what I'll be doing, and I'll also explain the theoretical part of the decoder. Sorry. So what we are essentially doing is we are randomly splitting the data just to avoid any bias. Now it is going to throw an error, batch size and block size. I have not defined it yet, but I'll explain what is the difference between block size and batch size. So you can see that um, we are separating the input x and target. So the way we do it is we'll be generating one character at a time. So for example, let's take the word this place is beautiful. So what we'll be doing is, let's say this place is beautiful, and then the next following L is going to be the target for all the phrase that was so far generated. So we'll be generating one character at a time. So I'll also give you an example basically. Sorry, missed an extra bracket. So I'm moving this to device. Now, what do I mean by that? So if there is a support of GPU, I would be moving it to GPT. Sorry, GPU. So return x comma y. Sorry, I'll have to define all this. So what is basically the block size? So the block size is nothing but what would be the character that would go as input. So for example, I love you. So let's say if this is a sample sentence, the block size is going to be what is going to be the sequence length: 1 2 3 4 5 6 7 8 9 10. So if we are considering the block size to be the length of this string, it's going to be 10 including the space, right? So this is one of the hyper parameter. So to illustrate this, for example, let's say that we have a block size of, let's say, 10, right? And we have a batch size um, of, let's say, 8, right? I'm just making it up, right? So what essentially happens is you would have a matrix, a tensor, basically. So that will have 8 as batch, right? And each of the row, right, will have a block size of 10, right? So this is basically what we would be giving as input. So all stacked together, sent parallelly to the model. That's basically how we would be sending the input to the model. So that's how it happens here in this code. But here, right, I just took the block size as 8 here, but what we are essentially doing is, in this model, the batch size is going to be much more higher. The sequence length is going to be much more higher. It's going to be 64. Batch size is going to be 64, and the block size, right, is going to be 256. So the batch is how many values do you stack, right? This part, right? So in this case, it's going to be 64 inputs that we'll be stacking, and then we'll be sending it out. And the number of, characters or sequence, right, that will be part of the first record, and the subsequent record is going to be 256, right? And then if there is availability of GPU, that is what we'll be using. So you can see, if it's not, we'll be using CPU. Till now, I've not gotten into how we'll be doing embedding, what is decoder, all that. I'll get into that in a moment's time, right? So post that, we'll start basically to construct the model, starting with the embedding layer, right? Because if you look at it, the very first layer of it is going to be embedding. One is going to be the text embedding, and the other one is going to be positional embedding. I mean encoding. Again, encoding is basically going to output a real number, which is embedding. We'll get there in a moment. So before that, we'll have to um, have a piece of code to evaluate, right? Evaluate our model on the validation set. which is what we'll be doing here. So we will be outputting what is the performance of the model on each validation set, provided we attain an interval. So if we have achieved the or attained the evaluation iteration, so that is also one of the hyperparameter that we'll be giving, right? So if we should attain that, what we'll be doing is we'll be performing the evaluation in the validation set. So you can see we'll be getting the batch. So we'll be calculating both logits. I'll talk about what is logits in some time, and also the losses. Loss is what is the difference between what we predicted and the target, the actual target. And for this split, we'll be updating our mean loss. Then we say model dot train again. Okay. So sorry. So if you see here, we are setting torch.nograd. The reason being, while we are evaluating, we don't want our model to calculate the gradient, right? Because it's not training, right? Why would it calculate the gradient? So hence, we don't want that to happen, and that's the reason we have this decorator. So I'll talk about the token embedding and the positional embedding. Let's first talk about token embedding. So what we are doing is we are creating a table, like it says. So it's going to have vocabulary size and number of embeddings. So number of embeddings is again a hyperparameter that we'd be giving. So in this case, the number of embedding, it's going to be around 384. Again, it's, you can give 384, you can give 512, right? It's up to you, right? So what we're essentially saying is, for each character, the output embedding, n embed, it's going to give 384 numbers. For example, I'll give you an example, right? So for example, let's say that so let's say we have A, B, C, D. These are like unique characters, and each of these is going to give you a number, right? Minus 1.06, comma 0.06, so on and so forth, right? This length, this embedding length, it's going to be 384. So if there is mention of any of these letters, we can just plug the embedding from this table and then stack it together, right? And then we could send that across for training. So that's basically why we are doing this token embedding table. And if you look at it, the very first layer here is embedding, so which is going to be the size of vocabulary size and number of embedding. So here, each of these is going to be like a sequence, and it's going to be this length, right? This row length, it's going to be batch size, right? And this is going to be added to the positional encoding. So why do we have to do this? Right? So let's say that we type some letters, I love you, right? That's like a sentence. It's going to be first converted to an embedding so that it can further be handled downstream, because models will not understand letters, it can only understand numbers. But we are also adding a positional encoding so that the words are understood with not just with respect to the input embedding, but also relative positioning is also represented by positional encoding. So I'll come to positional encoding in a bit, but the input embedding is basically your block, sorry, your batch, and then the width of it is going to be your embedding size. That is what you're seeing here, right? So whenever we'll be sending an input, and if there is a mention of a letter in the input, we would directly refer to this token embedding table and correspondingly pluck out that value, and that is what we'll be using in embedding here, input embedding basically. So I'll show you a couple of examples, right? So let's say that we wanted to access the embedding weight. So this is how we would be accessing the table. So the name of it, I mean, what is going to be the mapping? So I'm just sampling 5 characters. Just to understand what is going to be the structure of the embedding. converting it to list so that we could print that out. Let's see. Okay, okay, I'm sorry. Yeah, you can see it's basically the embedding table is 132, which is vocabulary size, and 384, right? And you could see what is the actual. I mean, we are sampling only the five tokens, first five tokens. You could see this is how the embedding would look like, and you could see the length of it, right, is 384, right? That's how many numbers we have. So as we go above the layers, each and every layer, we'll be adding one more positional encoding, and then we'll be adding both this embedding and positional embedding. It could have separate dimensions. PyTorch is smart enough to broadcast the missing dimensions, and then it will help us add. So for, I mean, to give you an example, the output embedding from the input text, let's say it's, I'm just making it up, let's say it's 64 cross 384, and the positional encoding is let's say it's 64 cross 128. Although you could see the second dimension is not compatible for addition, PyTorch would automatically broadcast and then make that into identical dimension, and then the addition is performed on top of it. So that's how PyTorch handles it, and I'll walk you through each and every detail. We are just done with this, right? We still have more layers to go on top. So okay, let's construct the head, right? I'll come to the positional encoding some point in time later. Let's first construct the head part, right? And I'll walk you through each and every step that you will be seeing on how we perform key value, sorry, query value, and then the key multiplication, and then how masked multi-head attention is performed, and what is multi-head attention and why do we need it. Okay, so I was telling you that I'll be talking about positional encoding in a bit. So here I've come. So first thing, right, I'll explain about the theoretical part of positional encoding. Post that, we'll be coding that in the model, right? While we are developing the model through code, we'll be adding the positional encoding. So, and again, remember, this is not at a token level. Our model works at character level. So just imagine each of these tokens to be characters in our case. And I've taken this screenshot from Umar Jamil's blog. So his blog is really helpful. So it's a fantastic blog. So I would recommend you to go through his blog. It was personally very helpful for me to understand how the entire transformer would work. So just imagine each of these are characters that we'll be generating henceforth, and you can see that these are assigned to an embedding. I was telling you about this embedding, right? You can see this is the vocabulary size, and this is basically the embedding size. So each character in this vocabulary will have a size of 384 embedding. Now what happens is, for example, let's say this character A, it will have an embedding of 384, right? And then we have the positional encoding. Now the positional encoding part, right, it's going to be of dimension block size, um, and your embedding, number of embedding, right? It's going to be block size, that is the character, and then the embedding, 256. Right, 256 is the block size, and you have 384, that's the embedding size vector. That's how we've hyper parameterized on in our code. So what happens is, you can see that already it's not matching the dimensions. However, like I said, right, the torch library, PyTorch library, it is smart enough to broadcast the missing dimensions, and it will add it up. So we will be getting an output vector where we'll be calculating the embedding, and then positional embedding gets added to it, and we'll be getting an output vector, which is then stacked, and that will be sent to the multi-head attention. Now, positional embedding is something that we calculate only once, and it is fixed because the position, it's not going to change. And the reason why we have this position is, the model would not only understand what sort of characters that would come in, but it should also understand the relative position of it. And if we are taking a sequence, the position is going to be the same, right? So positional embedding is only calculated once, and it is used throughout training and inference. So this is basically how the positional encoding is calculated. So you can see that we are using sine and cos, which is a trigonometric function. And let's say that we have sentence 1 and sentence 2. You can see that it's the same. We are only calculating once, and it is basically the same for both sentence 1 and sentence 2. For let's say that this is again for a theoretical understanding. Positional embedding formula can always be changed. It is in accordance with how you want to design it. But for example, let's say that typically we use sine and cos, which is a trigonometric function. You can see that it is based on position. Every alternate character will be alternating between sine and cos. You can see 2i and 2i plus 1, every odd position. This is basically how your position embedding is calculated. And every even position of the sentence, right, this is how it's calculated. Just to give you an illustration, let's take an example. Let's say we have in x-axis token 1 or character 1, token 2 or character 2, so on and so forth, still token n. And you have sign values over here, right? And basically it's going to be going like this, right? At this point, what is the value of sign is what is considered as embedding for that token, right? And same would also apply for costs, right? So it's going to be like this. And if you are thinking, okay, what if I'm getting a repeated value, that is not very likely, because as you travel over the x-axis, the curves are going to get broader, right? So that way, right, most often the values are going to be different. So that's how we are ensuring that the characters, right, they get their own unique positional embedding. So that's basically what is explained here. Next, we'll talk about the multi-head attention, right? You can see from this decoder diagram, both the input embedding, input for the character embedding and positional embedding gets added here, and it is sent to multi-head attention. I'll explain what is masked multi-head attention in a bit, but you can see that it is being sent here. And you can see there's three arrows, and this three arrows, right, it's basically for query, key, and then value, right? So I'll explain what is query, key, and value with the diagram. But you can see that input converts gets converted into word embedding or character embedding, and then positional encoding happens, and that gets added here. And then there's one big embedding vector, which is of dimension sequence or block size into embedding, that is block cross embedding. That's the vector that you will be getting. and after that you will have query, key, and then value. I'll tell you how each of these are generated and what is masked multi-head attention. So yeah, this is basically your multi-head attention. Once I've explained this multi-head attention, I'll come to masked multi-head attention. You can see that this input vector of size, sequence, and D model. Now, what is D model? Is basically the embedding vector size, right? In our case, it's 384. Sequence is 256. So 256 cross 384 is the input vector after adding your input and positional. Now, each of this, right, will have a separate matrix called query, key, and then value, right? These gets splitted into query, key, and value. Now, query is going to have a dimension of sequence cross D model. That is, in our case, it's going to be 256 cross 384. It's the same for all of the matrix here, query, key, and value. And that gets multiplied with separate weights. You can see WQ, WK, and WV, right? And if you see here, the dimension of it is D model cross D model, which is in our case 384 cross 384. And in any matrix multiplication, right, the number of columns of left hand side matrix should be equal to the number of rows in the right hand side matrix. That is validated here. You can see it's D model cross D model, that is 384 cross 384. Now that is, since that is asserted, you can see the output vector, right, row into column of the second matrix, that is sequence into D model, which is equivalent to the first query, right? So this weights are learned, right, in the process of training. So think of this like you have filters in convolutional neural network, right? It is pretty similar to it. So we'll be learning these weights in the process of training, and you can see the formulation here. The attention here is uh, it's basically a function, right? Given query, key, value, first query into key transpose is done. So when I say key transpose, again, what happens is, if you look at it here, it's sequence into D model, and sequence into D model. This gets transposed, so it's going to be D model into sequence. So let's take an example, right? For query, block size is 256 and D model is 384, right? And for key value, it is block size is 256 and D model is 354, right? So now, having said that, what happens is, if we transpose it, it's going to be D model cross sequence, that is 384 into 256, right? So multiplying both of these, this row into this column, that's going to be the resultant matrix, which is block size is 256, and since we are transposing it, it's going to be 256 here. So the output matrix is basically going to be 256, sorry, 256 cross 256. So that way, right, we get to learn what is the importance of each and every character with every other character, right? So it's going to be 256 character here, 256 unique characters here. Now this result is going to be in form of logits, that is, it is going to be in the form of uh, it's not going to be within the range of 0 to 1, it's going to be unnormalized. So what we do is, after applying q cross k transpose t, we will have to divide this by square root of dk, which is the embedding size. So in this case, let's say the block size is 384, right? So yeah, let's verify that. Yeah, sorry, block size is 256, right? The embedding size is 384. What we do is, we take square root of 384, right, and then divide it, so that it becomes normalized first, and then what we do is, we apply a softmax function over it, so that any range, right, any value, um, um, it gets converted to a value between 0 to 1. So we will then be able to understand the importance of each character against every other character with values between 0 to 1. And of course, right, initially it's going to be the diagonal is going to be more, because this character will have higher association with itself, right? So the diagonal is likely to be more than other values, right? So what we do is, once we've taken softmax, that is when we'll be multiplying it with value, right? Now now that we've multiplied that with value, right, this is basically the attention, right? So we first take query, and then we multiply that with k transpose, and then we divide this by dk, which is the embedding size, square root of embedding size, and then we multiply that with v. So we'll be getting a big vector like this, right? A big vector, I mean, we multiply this with v and we get a bigger vector. Now what happens is, we will have to split this, right? Split this into number of head size. For example, let's say in our case it's 384, 384, right? Let's say that we want to have four heads, right? If we divide it, we'll be getting 96, right? So we will have four heads, right? Four heads, one, two, three, four, and the dimension of it, right, it's going to be the sequence length, that is the block size, and this dk, right, dk is going to be 96. That is what you're seeing here. So this one big vector is split into chunks, right? Chunks of head size. So 384 is divided into 4, and that is what you're getting as vector here. So why are we doing it? Because each head should have access to all the characters, but only a portion of it. You can see that each head will have access to the entire block size, right? The 256 block size, but it is only going to have a portion of the sentence or the phrase, right? So if you can see, the multiplication happens at individual head level, right? So there's four heads, and query multiplied by k transpose, that is key transpose, divided by square root of dk, which is the embedding. Softmax is applied, and then it gets multiplied with this v1, that gives the result of head 1. Like this, head 2, head 3, and head 4 happens, and then everything is horizontally stacked, if you see. Then we will again be getting this value of sequence into dk, right? So if I mean, again we'll be getting the value of the embedding vector, right? We are back to square one, sequence to d model. um, that is what you're seeing here, right? And then there is a weight that is applied further, that is the output of the first multi-head, right? So this, again, this is a learnable parameter that we'll be learning in the process of training. So is these values, right? And this is basically going to be giving us importance of each character with every other character. Let me illustrate this with an example, right? Sorry. So yeah, so for example, we have love. Let's take genres, right? Love, crime, comedy, right? Comedy. So these are genres, right? And then let's take this as query, right? And then we have key. Let's say key is movie name, or let's say character name, right? Let's say love, right? DiCaprio, right? We have DiCaprio, and let's take um, yeah, comedy, right? Catch Me If You Can, right? Again, DiCaprio, right? And let's take a crime, right? So maybe um, Mark Ruffalo, Hulk, right? One who would act in Marvel Hulk, right? Let's say Ruffalo, right? That's the name of the artist, right? So you have query, which is love, crime, and comedy, and you have key, right? And then let's say you have value. Let's say value is Titanic. Um, you have um, right, and then you have um, catch me if you can, catch me if you can, um, and then let's say um, um, I don't know, this crime series, right? Sorry, crime movie, right? That has Mark Ruffalo, Zodiac, right? Zodiac. Let's say Zodiac. So what happens is, let's say we have love as a query, right? And we multiply this query with all keys, and basically what happens is, for love as query and DiCaprio as key, right? Titanic would have more affinity, right? It will have a bigger value compared to Zodiac and Catch Me If You Can. And if you have query as comedy and key as DiCaprio, Catch Me If You Can, right? And when you have crime as query and DiCaprio as a key, right? Probably, right? These are going to have lesser values. So this will help us understand what is the affinity within characters, right? In our case, when we are sending this to the model, and that will help the model understand the relationship between characters, and that will help the model predict what would be the next character given a set of characters, right? So that's the reason we have multi-head attention here. So that's what is basically explained here. You again, right? It's color coded here, but I guess I've explained it with movie names. And what is essentially multi-head? Like I said, right? If you look at it here, every word, the diagonal part of it is going to be more. Now we are not using encoder decoder model because, again, like I said, GPT is generative given a set of words. So we are only using decoder here, and you can see there is masked multi-head attention. So what we are essentially doing is, we are sending these words, and anything above the diagonal, right, initially we'll mark that as minus infinity. So and if it is soft maxed, it all these become zero. The reason why we are doing it is, we'll be generating one character at a time given a set of characters. So one character should not have access to any characters in the future, so that the prediction becomes smoother. So you can see that all the elements above the diagonal is marked minus infinity, and when it is soft maxed again, it becomes zero, and anything multiplied by zero would also become zero here. Let's say even if it's getting multiplied by v, right, it becomes zero. So that's basically how we are dealing with when we are generating the decoder network. Hope this was helpful. So this is where we'll start training the model. You can see that it's a baby GPT, so it's nothing compared to the models that has billions of parameters in it. It's just in millions. So I've started the training. It's going to take some time. At least it will take 10 minutes, right? It's going to take a couple of minutes because I'm training it for 5,000 iterations, and for every 500th iteration I'll be evaluating, and we can check the validation last thing. So we'll return after training. Now that we've gone through the query, key, and value, and how it plays in self attention, let's work on coding these aspects and putting that into a model. So we'll start coding the head. You could see that um, I am inheriting NN module from PyTorch. So yeah, it's just one head self attention for now. We later multiply it. I mean, for different heads. So this is a parameter that we give, head size. This will determine how many. I mean, what would be the head size? That is, I was telling you, right? What is going to be this outcome of these columns? My bad. So we are now configuring the key query value. You can see that I'm just using a linear layer. All these, just imagine these to be a matrix. And if you remember last time, it's number of embed, right? That's a sequence length. So this is self dot register buffer. You could. I was talking about the triangular matrix here, right? And that is actually what we are doing here. You can see trill torch dot util. Sorry, torch dot trill torch dot ones. That will be equivalent to block size. And we are adding dropout. So to avoid any overfitting. Okay, so I'll explain what are these. So this is batch, right? So batch is basically, I was telling you, right? So we will be sending inputs in batches, right? Stacked one above the other as one big matrix. So this is basically going to be 64, right? And then we have the token, right? The basically the vocabulary, right? And then we have the channel. Channel is the embedding size, right? So that's how it is split. So we are getting the key here, and then followed by query x, and then yeah, we will be calculating the weight. So this is for dot product. So I was telling you, right? We'll have to do a transpose, the last dimension, so that the output is going to be sequence cross sequence. So yeah, I'll put the output here. So it's b batch, and then token, and then the channel hs dot product with b batch token, and then sorry, batch channel and then the token. So which is going to give us batch cross, sorry, yeah, cross token token. Then we have weight, and this is where we mask it. We'll be masking it with minus infinity, like I said, and doing so we will be getting 0 when we softmax. Yeah, triangular matrix. Now again, it's going to retain the same dimension. Now is when we are soft maxing it. Still going to hold b t t, and then we'll add a dropout. And then we will be doing a multiplication of value output is a dot product of way, and then v return out. Now if we are doing it, the input is going to be b slash t dot product with b comma t comma h s, and it's going to give um, batch token, and then hs is going to give you row of the left hand side and column of the right hand side, which is going to be b token hs, last dimension of the right hand matrix. So this is basically, yeah, just give me 1 second. Yeah, okay, I'll have to rerun everything since we've timed it. Sorry for that, because I'm starting this session fresh, so hence, right, it's giving us an error. Okay, now then, let's code the multi-hit. Attention, again, inheriting the torch. So here is where we'll be getting what is the number of heads, what is the head size. So you can see that we are using four. Sorry, we are using relu for activation, just like in the paper. Finally, I'll go through the entire model again, the architecture. So I've given some configuration wrong. Yeah, sorry, my bad. An embed, it's not consistent. My bad. Yeah. Then let's configure the whole block. So we will be basically, we've just done masked multi head attention. So we will anyways be adding normalization. I mean, we'll be adding the layer norm on top of this, which I'll be explaining it in a bit. But what we are essentially doing is we are also constructing the feed forward here, because you can see that from masked multi head attention, it goes to a layer normalization, and then followed by multi head, and then layer or normalization again, and then it's getting fed into a feed forward, and then layer normalization, and then it goes to a linear layer, then to softmax. Now they are only showing one decoder here, so but we'll be adding six decoders. But right now we'll be coding the feed forward neural network. That is, we'll be stacking one layer above the other. We'll be constructing this whole head actually. So this is basically adding what should be the number of heads here. So I was telling you, right, this part wherein what we'll do is you have the D model, which is the embedding. So let's say we want four heads, right? What we'll be doing is, and let's say again, for an example, okay, I'll show you one example here. I'm taking the embedding here. Yeah, number of embed is 384. Let's say this example. So if it's 384 divided by number of heads is, let's say 4, it's going to give 96. That's going to be the dimension. So each width of this head is going to be 96, and 96 into 4 is going to give you one big embedding vector, which is again 384. So that's why what we'll be doing is we will be calculating the head size, embed integer division by number of head. Self attention, SA for self attention, you can see multi head attention is equal to number of head. In this case it's 4, and head size, it's going to be 96 basically. So which is 384 divided by 4. Basically it talks about this one big block, wherein sequence is going to be the whole block size 256, and 96 into 4, which is going to give you 384, and then followed by a feed forward neural network which would take nembed 384 as input, a linear layer for normalization. I'll talk about what is normalization in a bit. So again, this is for skip connection. So I'll talk about this in a bit. Okay. So if you look at it, right, multi-head, after multi-head attention, there's feed forward and then a layer norm. There's two layer norm layers, and then what we do is, this is basically for the skip connection. So what do I mean by skip connection? You can see there is going to be, after multi-head, this normalization layer, and you can see this output is again getting skipped to this layer norm, and then from here it goes to a feed forward, and then here there's a skip connection to another layer norm, and this will get added, and that is exactly what we are doing here. You can see this feed forward, and then this L1, ln1 and ln2, which is layer normalization. So you can see this one coming from input added to a layer norm that's coming out of self attention here, right? Layer norm input, this one getting added from multi head, and then to layer norm, and then from here it's getting added to here, right? Which is what we are doing here, right? So from feed forward, we'll be adding this to another layer norm, right? So it's this connection, right? It goes to a feed forward, and from that feed forward there's a skip connection here to another layer normalization. So what is basically a layer normalization? um, so in statistics we have this concept, right? It's called normalization. When we have these parameters, we have the whole feature, we take the mean out of the whole feature, and we negate that feature value with the mean, and then we divide that um, with the standard deviation, right? That's basically what we do. And that's exactly what's happening in layer normalization here as well. And apart from this, there's two other parameters, alpha and gamma, which gets added to the normalization. But this alpha and gamma, it's a parameter that is learnable through training. So that's the only difference here in terms of layer normalization. We've constructed the block. Now let's actually construct the whole GPT model. Let's assemble all these blocks together. That includes your head self attention, multi head attention, and then this whole block together. can see we are constructing the token embedding table using vocabulary size, and then uh, that is unique set of characters in the corpus by embedding number, which is 384 in this case. So here we'll be adding more blocks. um, yeah, again it corresponds to the number of layers that we want, so we'll be adding 6 blocks just to mimic the decoder architecture. So we'll be applying the weights. Now you could use any weight initialization, any method, like zero initialization or Xavier initialization, but that's up to you. You can see that we have a function for it. So not everywhere we'll be applying the weights. Only those layers that has learnable parameters, we will be applying the weights. Here we are using normal initialization. With a mean 0 and a standard deviation of 0.01 maybe. It's pretty much the same. We are not using a different method for initialization when it comes to embeddings. Now let's work on the forward pass. Patch, and then we get the token. Again, it's going to give PTC patch token and then channel. Yeah, you can see that we are adding token embedding plus positional embedding like we did before. So it's going to give B, T, and C. So I was talking about this step, correct? So we'll be adding the output embedding and then positional embedding. That's exactly what we're doing here. It's going to be the output dimension. Then we are calculating the logits. So B, comma, vocab size, which in this case is unique characters, the corpus. This is for inference when we don't have a target, because we will, while inferencing, we'll not have a target. Otherwise we will have to calculate the loss. We are collapsing the first dimension. Target will only have one character at a time for batch. We are using cross entropy as cost function, which is for negative log likelihood. Okay, now we are done with forward pass, and we'll also write a method for generating, post which we'll do training. So this parameter is for how many tokens, in this case you can say how many characters. So it's going to be an array of ht context for range max new character. So we'll be getting the first block. So this is where we get the prediction. -1 comma, this becomes, and then we'll get the probabilities after applying softmax, which is going to give a value between 0 to 1 for each indices of the character. Still channel, batch channel, and IDX next. So this particular line of code has a significance. I'll talk about its significance. Basically, what we are doing is we are sampling in the output probability. But I'll basically explain this when we are doing inference, because this is analogous to chat gpt temperature parameter. When you are using chat gpt and when you want to randomize the results that's coming out of the prompt that you are giving, this particular line of code mimics that logic. So it's going to sample probabilities that are usually higher, right? And it's always not going to give you the maximum probability, but it is going to sample from the top probabilities. So each time you give an input, the output is not going to be the same. Okay, so this is basically it. Okay, my bad. Okay, okay. Let's look at the training in the upcoming session. So we have completed our training process. You could see that we are converging around 1.21. That's a validation loss. You can see that we started with a very high 4.90 validation loss. And after 5,000 iterations, we've converged to 1.21, which basically means that we are off by 1.21 characters approximately, right? So the way it's calculated is, let's say that we have logits, for example, 0.9, 0.01, and zero point 0.8, comma, 0.001, right? Let's say this is our logits, final logits, for 4 characters for simplicity's sake. And we have the true label, something like this, right? So the way it's calculated is, first thing what we do is we take log base 2, right? That's what we take. So it's basically going to be um, np dot sum of, um, yeah, so this matrix, let's say this matrix is, let's say our target, right, is equal to this, and our prediction, right, is going to be this at a particular timestamp. So then what we do is, um, we take target, and then we sum it, and then we take np log, sorry, log of the prediction, right? Okay, I'm sorry, my bad. Yeah, you could see that this is basically the loss. We are very close, right? This is basically how it is calculated in terms of loss. So first thing, it takes log of this. Again, we have to be very careful. It's base 2, right? And let's say this is the target, and what we do is, after taking the log, we multiply it, and then we take negative sum of it. So you can see, right, pretty much every value here would be 0 except for 0 0.9, and 0 0.9 log is zero point 0.9, right? It's minus 0.15, right? So what we do is, we sum it, and basically that's what we'll be getting. So this is how cross entropy works, and by doing this, we could see that we are off by close to 1.21 characters. Not bad, but there's still some improvements that could be made, right? And this is basically the inference part of it. Let's say that I'm just giving 0, probably it's for space, right? And then I'm generating 500 tokens. Yeah, this is what you'll be getting as output, right? So it definitely looks like a cinema dialogue, right? Hey, that's what, why it's nice a small road to go start. Again, it's I mean, there's a lot of grammatical error, because we are doing a character level generation, it's not a word level generation, so it can only understand what is the relationship between characters and not essentially words. Right, so let me give something like this, right? How beautiful is India, let's say. Yeah, see, hope and on the sun has right alone, that was through the door we found, I'll kill somebody when I decided you, that's too big gesture. I mean, it has no connection with whatever I've typed, but you can see that at least it is forming words. And but as a whole, right? It's not going to make a lot of sense. Now, with the same input, let me try inferencing one more time. Yeah, you can see, right? I've given the same input, but this time it has written something different, right? Why did it do so? Because the weights are fixed for the model, but still, why is it giving a different output? The reason being, it's because of this line, right? You can see that we are doing a multinomial sampling out of the probabilities that we are getting at last, and that is giving us different outputs each and every time that we do inference on. And this is very identical to the temperature parameter of GPT. It actually behaves very close to it. So that's how we are simulating it. And I told you that I'll be showing you the whole model construction, right? This is it, right? You can see that. Okay, maybe I'll have the decoder, right? Transformer network beside this. Sorry, my bad. Yeah, this is basically it. And we are only focusing on the decoder part, not the encoder part, because we are using only the decoder. To start with, we have the input embedding layer and the positional embedding, which is what you'll be seeing here, right? You can see its vocabulary size with embedding length, and this is sequence length or block size with embedding length, which is what you'll be seeing here. You can see that it is getting added here. And then we have multi-head attention, right? That is what you'll be seeing here, multi-head attention, and basically a feed forward network after that. We are anyways having a linear layer here before the feed forward, um, which is what you're seeing here, right? And then what we do is we send this to layer normalization, yeah, which is what you're seeing here, right? So like this, we've stacked 6 multi-hits, starting with this, right? And it goes on like this till 6, 0 to 5, which is 6, right? And then we have layer normalization, and then we have a linear layer of 384, again the embedding size, which is what will be soft maxed for calculating the cross entropy. So this concludes construction of GPT model from scratch. So thanks a lot for watching.